All right. Thanks, Jeremy. I'll try walking around just because I like to wander a little bit and point instead of, I'm not very good with the laser pointer. I don't never feel very confident trying to show you what I want that way, but we'll see how this goes. What I'm going to do today is walk you through a little bit of process. Hopefully this, gets your interest a little bit because it has touchstones in a lot of ways, maybe to almost every talk that we've seen the last 2 days, just in the way I'm going to show you some of the informatics or bioinformatics. So, a lot of you are interested in tracking variants of T-cell binding epitopes or underlying genetic code of some sort. I'm going to talk to you like that, but at the protein level and the way we address a couple of things. So a couple of perspectives. I'll kind of give you the regulatory perspective a little bit. Of course, I'm coming at it from the industry side in the way we have to address safety for biotech proteins and the way we do that thinking about allergy safety. For the paper I'll talk about a little bit, I have a kind of a more refined title, but I left this one up the way it was. It may seem a little redundant to you, but I left the immunologically relevant cross-reactive piece in there because it pertains to the way we have built over the years what we call our qualified allergen database. So I'll start right away with kind of the hypothesis that kind of drove looking at a process for how we're going to look at allergens. We have allergen databases that's mostly taken care of by peer reviewers in the food allergy science fields, and they go in there based on clinical relevance for individual proteins that have enough, enough information, typically based on serology from qualified patients with a good patient history. But the question is it possible to better understand allergens using informatics? So we know allergens are special proteins. Like I said, we have a qualified allergen database, so we know they're special clinically. We don't know a whole lot about them biophysically or biochemically, or not as much as we'd like to. But what we do know is they're constrained in a taxonomic way. Part of the regulatory guidance for addressing biotech safety as it pertains to allergens is that you have to make sure you're not an allergen if you're going to use it in a food item in a new way. But you also have to address whether it's going to be cross-reactive with existing allergens, and that's mostly what we'll be talking about. As you know, when you are talking about elicitation hazard and cross-reactivity, it's of course focused on the localized epitopes. That would be the IgE-binding epitopes if we're talking about type 1 hypersensitivity. The tricky part in trying to assess this systematically with bioinformatics is, of course, the epitopes themselves can be in different states of presentation. They could be linear epitopes that are just presented fine once, say, a food protein is digested, but many times you're dealing with discontinuous epitopes. And one of the struggles over the years with thinking about regulatory guidance is that if you ever asked, is one protein like another, you're basically asking whether the percent shared identity is above or below a certain level. Pretty rudimentary. To do any kind of bioinformatics traditionally, and again, this is kind of going in the Wayback Machine to the 20th century in compared to what most of you work at algorithmically, but of course, BLAST and FASTA have been the tools of choice for asking any of these similarity questions. So you can perform sophisticated nonlinear estimates of how similar two proteins that get far beyond just shared identity and really address similarity. And for all intents and purposes, you would do that just as you would with any assessment of similarity across groups or families of proteins. So the safety perspective, if you will, regulatory guidance, like I said, we've basically had this in place for about 20 years. And back when that came into being, you had food protein scientists that maybe weren't bioinformaticists having the goal to draw some line in the sand about asking whether similarity was above or below a certain amount. And the numbers that were chosen were 35% over an overlap length of 80. Deemed conservative, knowing that it wasn't probably accurate across different groups of allergen. At the time, and still our biggest group of cross-reactive proteins in a family, if you will, are the Birch tree pollen allergens, and that's more or less what that was based on. Again, pretty rudimentary, didn't take similarity to account, but those numbers became embedded in what we use even today for regulatory guidance. So the way I would look at this bioinformatically is it's a problem because we know we have lots of allergen groups. And in fact, the allergen database that I refer to, about half of what's in there you would call orphan proteins, where you maybe only have one or two members from a structural protein family. And they're allergens, but all the other members of that structural class are not. We don't know why, but more work needs to be done to really understand that. So we've got kind of a, it's not a one-size-fits-all situation as the 35/80 would suggest. Allergens are diverse, but yet asking this cross-reactivity question is difficult because we don't know most of the IgE-binding peptide or epitopes for most proteins, and for those proteins where we know they're cross-reactive, maybe in a group of patients, we don't know why, or that mapping of the cross-reactivity hasn't really been done. So, bioinformatics, a lot of you, this will seem very simplistic. Putting this together, part of my audience are people that don't have the skills of the folks in this room, but I at least wanted to show you that when I say identity and I'm using a tool like FASTA or BLAST, where those numbers are coming from. And it's just to highlight the fact that we've got this kind of very baseline rudimentary guidance based on exact matching and calculating a percentage score. But what we really want to do is use the power of these tools to estimate how this protein would really fold and have similarity, and use the statistical power of the tool to get at really understanding similarity in a more practical or accurate way. So, bioinformatics and allergens, the premise, if you had a good empirical evidence data set that coincided with known cross-reactive epitopes, then there'd be better support for drawing a new line in the sand, essentially. So what I'm really telling you about is, and I'll walk through a process that would give us some better understanding than trying to deal with this 35/80. And we, different groups have published on using BLAST and FASTA and the way we do this for regulatory guidance. And it's pretty well understood that 35/80 is so arbitrary that you can actually have that be observed for random sequence. And so that's a problem because you want to be conservative, but you have to be accurate enough for it to be useful. So my question for what I'm going to show you is how would I test whether, and I'm going to use FASTA, but could it be other local alignment focused informatics? There are much more sophisticated, motif informatics you can do, hammer, but I have to kind of work around or in a context in which the regulatory community can operate, and it's going to have to be something they're familiar with. So FASTA, can it find a level of similarity in known allergen groups that would make sense? There's a couple of secondary premises here. As I mentioned, we don't fully understand allergens, so we don't have that single set of biophysical parameters where I could predict when a protein's an allergen and when it's not, even if I use my allergen database as a trainer set. You see some of the things we pay attention to up here, like pepsin enzyme stability. Those haven't gone away. We still characterize a novel biotech protein with those because we don't have that predictive capacity yet. Well, what's changed now is there's a greater reliance on the accuracy of bioinformatics. It's like I said, it's gotten pretty sophisticated as we've seen through some of the other talks here. And so I want to be able to use something though that's accurate, still protective, so I can do allergy risk assessment. So we know we've got better bioinformatics. We want to use those to hopefully upgrade what we're dealing with in terms of regulatory guidance. one of the things, and I'm just giving you an example here in the next couple of slides about, I find it a real challenge communicating bioinformatics, partly because it's kind of it's a statistical algorithmic function to try and say something about whether something's alike or not like something else. And one of the things you run into is, it's not difficult to do what's been done on this slide, which is to call out the taxonomic relatedness amongst a bunch of organisms that produce a protein called profilin. And it's also pretty straightforward to call out the group of those profilins that are allergens. But then, the question would be, well, if I've got a profilin, certainly by name, it's implicated as an allergen. Well, no, that wouldn't be the case. So, in this example, we know that only plants produce these allergenic profilins, and they're also highly related. So within that group, you can get at cross-reactivity, and you can do it even better if you knew the IgE-binding epitopes within that group. But they're widely distributed, and so it's a challenge to use bioinformatics to describe when you should pay attention to cross-reactivity potential and when you shouldn't. And so, the point here is that you can use bioinformatics in this way to sort out that relatedness. The relatedness in and of itself, just because I compare two sequences, doesn't necessarily prove cross-reactivity. It certainly wouldn't prove that a profilin from mouse is an allergen just because it showed up in that taxonomic tree. So just my point there is that it's a bit of a communication challenge. It's not, bioinformatics itself is not an end-all. Usually I say it's a starting point for if you see significant similarity, then you can do something that gives you better proof of positivity of cross-reactivity. Really what we're doing with these informatics is interpreting higher levels of similarity. And so, and the premise that I'm getting at here is that we want to pay attention to the IgE-binding epitopes. Why? Because programs like FASTA and BLAST actually do a really good job, we know they do, of finding interdomains, if you will, within a larger protein. And they can show you that, they can find it, and give you an estimate of the statistical probability that those two proteins are similar. And so you're not always paying attention to the whole protein sequence. And so you've got a biologically relevant portion if you know it exists, meaning if I know an IgE-binding epitope is in one protein, I can ask something important about that epitope. So the goal was simply to improve the evaluation of alignments. I showed you just a basic alignment before. You get some standard statistical output from that similarity assessment. And so I want to use that same thing and ask, is there something there we can use that's better than a percent identity score? And so we need a little bit of a process. I need to know, if I could, I'd like to know how all the allergens are alike or not alike. When are they different? And is there some kind of common threshold for describing similarity? Meaning this last part here is, can I actually find a new line in the sand with bioinformatics where I could ask that for any allergen? We're not there yet. I'll give part of the answer away already. We're not there yet, but I'll show you where we can actually get at some of this. And it's just so that we can find and sort, right? We want to find where two proteins are similar, and we think we can do it based on IgE-binding epitopes because that's our biologically functional unit that we do have some information on for some proteins. So, two protein allergens may share a portion, but not their entire sequence. And again, it's around asking this question of cross-reactivity potential or hazard. And then, is the degree to which one sequence is similar to a known allergen measurable? And can I use that kind of as a standard measure? So I'm going to use output from FASTA. I'm going to compare known epitopes. So I'll use that as my surrogate domain, load it into sequence, and I'll select epitopes that are from known allergens, of course. And I know from these programs, and again, I'll focus on FASTA, that the E-value, and I know we've seen that on some of the slides, the expectation value, that is essentially the penultimate summary statistic from, say, FASTA and BLAST. And so, again, this is what we're going to focus on. And I'll just say as a side note, when you have databases that are large enough, and this will give some of the numbers context, the expectation values function like p-values. In fact, they are probability values. So in your head, when you see an e-value, just think p-value. If you start to see values below 0.001 or 0.05 even, then you should start paying attention to similarity. Design approach for actually asking this question is I'm going to spike random assortments of amino acids, so completely arbitrary sequence. And I'm going to do that with IgE-binding epitopes, and they're going to have these two features. I'll go ahead and make a hypothetical protein that's the same length as the protein where I derived IgE-binding epitopes. So I'll keep the end-to-end length the same. And the epitopes, of course, will be real epitopes, and they'll be placed in their concordant placement from the C-terminal end. So they're in the same place with the same spacing. It's just the surrounding sequence will be completely random. So I'll end up with a hybrid or a hypothetical sequence, and I can now ask, is just the IgE-binding epitope, apart from any of the rest of the sequence that would normally lend all that structural conformation to make that protein unique, can I actually get down to as low as an IgE-binding epitope and still find myself in a pool of sequences? Meaning myself, I'm an allergen, but my only flag is an IgE-binding epitope. So the first one I'll work with is, like I mentioned, the one that really was used to drive the original regulatory guidance, and it was the BET-V1 discontinuous epitope. And you'll see kind of the design here. We've got a pretty short protein, 156 in most cases. We've got a lot of them. This one's 160. And the 16 residues of the discontinuous epitope, that's not very much. I did a couple of things. I did use just the 16, which have the underline here. But I also, before I set this up, figured, well, that may be so little I won't get very much useful information. I'll use the region that also includes the 16 residues. So that's why you see both the underline and the highlight there. And so that then is a hypothetical sequence I can work with, but it's loaded with known epitope structure. The other example here with tropomyosin, this one is much longer, and it's the linear epitopes are many, so not a discontinuous epitope, but several linear epitopes. That's one difference. The other reason to work with tropomyosin is you might expect something different for the output of this because tropomyosins are highly conserved, and you see that across different species of, say, shellfish, where you know you have allergenic food source and it's based on tropomyosin, taxonomically very conserved. And so different than some of the other proteins I looked at. So what we're going to do is send these hypothetical proteins back against our allergen database. That database has been peer reviewed. We know that that's a qualified set of sequences. Not to mention that the tropomyosin where we got the epitopes also exist in that database. And so we want to ask, at which threshold does the E-value distinguish known cross-reactive homologs? So in the case of tropomyosins, I would be seeing potentially a lot of other tropomyosin, but just from other species. And does it then separate cleanly or not from just other proteins where similarity exists, but they're not otherwise tropomyosins? And so we can do that if we've got allergens that are well studied, good clinical data, and of course, if we know the epitopes themselves are the reason there's cross-reactivity in that group. Secondary question here, but again tied to the regulatory question at hand, when does the 35% over 80 criteria that we've always lived with here in the past years start to lose relevance if you believe or trust the statistical assessment of these real biologically relevant epitope sequence? So here's a summary table, and as you've seen from my Bet V1 or Betula species example and tropomyosin. I'll focus on those two, but here's a table with several proteins I looked at. And so sending each hypothetical protein with the epitopes loaded from each protein represented here, all I'm showing you in the table here is the highest, most significant E-value and the lowest. And what it does is it gives you a sense of the range. And the most basic question here is, do I see kind of the same top end and bottom end for each protein, or is there a difference? And so I usually want to pay attention to the least significant, because least significant would be where maybe I draw a new line between significant homology with, say other members of this protein group and where things become irrelevant statistically. So I've got 10 to the negative 10th, 9th, then I skip down or skip up to 3, and then even 1 here, and then back down to 11. So there's not concordance across the proteins that I chose. Just highlighting that with red boxes, but I've hopefully pointed that out for you there. How am I doing on time, Jeremy? So let's go back to the Bet V1 molecule. I looked at the one where I highlighted the whole 56 amino acid region and then asked that question about this line in the sand, or commonly, folks will refer to it as a threshold. And again, mostly paying attention to E-value. And here you can see that it belongs to a group of proteins. They're no longer necessarily called Bet V1, but these PRP or pathogenesis-related proteins, those are fairly consistent in being represented within that structural class of protein. I'm right here approaching the borderline of what the authors of the FASTA algorithm say you should pay attention to. And then there's a pretty clean break here, at least in E-value. And I start to have irrelevant similarity in terms of the class of protein. So in that case, a pretty clean line in the sand with our largest group of molecules in the allergen database where we know cross-reactivity exists. Here's the tropomyosin example. Now there are lots of tropomyosin molecules in the allergen database, so I can't show them all on the screen here. And just as before, it's sorted from smallest value, but highest exponent down to lowest. And there's a clean break here, and I actually don't see any other proteins. So only tropomyosins show up when I use the tropomyosin epitopes, and the E-value is shifted much lower than the -3 exponent that you just saw for the Bet V1. And that's what you might expect. I told you that it's a large molecule, but really highly conserved. And you would suspect that the epitopes themselves across the different tropomyosins are conserved. I didn't actually look at that, so I can't tell you how conserved or what the variance in epitopes is. But I think with this, at least, I kind of got what you would expect for that class and the way the taxonomy works with tropomyosins. So then I mentioned one of our kind of secondary questions or premises here is that we've always suspected, and through other publications know, that this 35% over the 80 overlap, arbitrary, doesn't perform very well, and you can get it to fail, so to speak, when you run it many times and start to look at arbitrary sequence. Well, I can look at that question here. Here are the tropomyosins, and this is drilling into that big long table more than what I just showed you. And I've got the percent identity and overlap right next to it, to the E-value. And you can start to pay attention where I'm below 35%. Here I'm over, so there's a good match, but where it's grayed out, I lose that matching. And so you can see just by eyeing this table that the majority are reflected, the homology is reflected with very low E-value scores but not very many of them do I have a concordant 35/80, meaning I'm gaining accuracy by setting up, at least asking whether I can set a threshold for the tropomyosins and paying attention to our existing criteria and asking where E-value might be useful. So fairly clear in my mind that 35%/80, at least from from a safety perspective, wouldn't protect you per se if for whatever reason you're working with a novel protein and it was a chimeric in such a way that you actually had some novel sequence because of the adjoining, and you did want to look at that against your allergen database just to check that for whatever reason, if you incorporated 1, 2, 3, who knows, just by chance, epitope structure there from tropomyosin, you might not find it. So we're back to just asking, do I have a process? And by process, I mostly mean I have not taken every allergen structural group in our allergen database and done this work with it to construct hypothetical proteins. What I wanted to do was do it for the 5 or 6 proteins that I did focus on, ask the question, ask what the performance of the algorithm was at its just most basic level, but using a better statistical parameter to set this up possibly for doing this more thoroughly so we can get at this and actually work with the next time that we're able to get codex together or FAO, WHO together when we actually pay attention to our guidance around this area. So I'm setting up as still an open question just because I haven't done this with all the allergen groups. But it's just a basic question. What can we do better with bioinformatics to do this thing that we're already doing with this allergen database? We've done a pretty good job of putting the allergen database together. We have a running consortium of experts in the field to help us rebuild that database every year. It's just the bioinformatics could be better. And so we know we need to understand the allergens themselves better, how the database is made up at the sequence level. Certainly epitopes have not been discovered for most allergens. That would, of course, make this work even possible. And then, ask even with more sophisticated tools, what are the features that make up a high-quality alignment? So I really want to get past the percent identity and overlap, focus on E-value and some other parameter that maybe with more sophisticated algorithms might improve on that even, because there's certainly nothing new about FASTA E. I'll leave it there and take some questions. Thanks.
Thank you very much, Scott. Yeah, great. So I guess going back to the tropomyosin data, from the point of view of all those different species that are expressing that protein,
right?
How many of those do we know are obviously, because most people aren't going to be exposed to those particular tropomyosin proteins, but do we have any idea of actually, in reality, how many of those might actually be allergenic?
So all the tropomyosins are allergenic because those are represented in the allergen database.
Right.
So I didn't send that comparison out to the broader world of, say, known protein sequences. So presumably, although it's not 100%, but presumably all those proteins have at least one representation in the literature of one person, a patient, through serology that showed, IgE reactivity.
Right.
Yeah.
Yeah. So the fact they've got very, very low E-values, does correlate with
It correlates, yeah, and it just happens, I think, to correlate well with the tropomyosins. They make a good group of proteins to look at because we know of a lot of them, and they're so highly conserved, just taxonomically.
Yeah. So what's next for you in this kind of project?
So we've got other groups of proteins in the allergen database where we've at least can have a representative sequence where somebody studied the IgE-binding epitopes pretty well. That would be the next step. I can't even tell you what number of proteins that would give me to do this work. It's still going to leave behind the bulk of the allergen database because we just haven't done the IgE mapping work. The world hasn't. But I would say if I could do another 5 to 10 model allergen groups and do this same work and get the right regulatory audience in the room at the same time, and kind of leverage doing, better bioinformatics so we can get past the 35 over 80. Yeah.
Thank you. How important are post-translational modifications, especially on plant peptides that might be cause a IgE reaction?
Yeah, I mean, you probably have to go back to 2000, 2002, where I think people thought the worry of, the glycan moieties were a possible causation of, allergy elicitation. I think now, and there's been some folks, particularly in Europe, that have studied that, and the conclusion, even with model proteins, is that post-translational modification that results in some of those sugar moieties, like N and O glycation, are not eliciting factors. You can find IgE that will bind a sugar moiety, but it is not the eliciting factor, it's the protein. So from the safety perspective, we've got kind of a basic post-translational, like a Western-based immunobinding assay to check that for biotech proteins, but it's the weight of it in the risk assessment is very low, just because it's understood that you can't track allergy potential by looking at post-translational modification.
And then
at least for that focused type of post-translational modification, I guess, I'm a qualifier.
I'm getting way too much information. My dad's a cotton farmer, so Roundup Ready cotton, for instance, is something you see Roundup on a lot of, Roundup resistance in plants.
In plants, yeah, sure, or weeds, yeah.
So that must have been studied in depth to understand if there's an allergic reaction potential to that protein.
Right.
Yeah. How sophisticated do we have to be? I mean, I guess I wonder if you could just sort of take it one peptide sequence at a time, just build cassettes and try it like a basal test assay, or do we miss things by doing? Do we miss things that are driving IgE responses by doing that?
So your question is about allergy, but how does the weed resistance itself come into play for you, or what?
Oh
what
no,
do you
I
think?
was just thinking about just taking the protein and and just testing it and just finding out by just sort of building a cassette of peptides all the way down the thing to see,
Right.
Is that definitive enough for the FDA?
Well, yeah. So
FDA,
what you'd be asking is for something, if you knew that you had somebody in the world that was seropositive for that protein, right?
Yeah.
But no one is. So how, you would have to ask the question, I could, of course, make the peptides, but what would I be mapping? Where would your IgE come from?
Right, well, that's the kind of conundrum. It seems to me that they're sticking you with 35% over 80 amino
Right.
acids as some kind of criterion, when you could actually just kind of directly show them, hey,
Well,
we tested
I can,
1,000
yeah, well,
samples.
I can tell you what we want to do is to be able to use better bioinformatics first, because that's always your first, but it's also the last screening activity you would do, right? And so I would argue you want bioinformatics at least to be in your first tier, because if you don't otherwise, and in that case, there's a lot of understanding where the EPSPS molecule comes from, and basically every plant has an EPSPS. So there's no understanding of hazard there to begin with. So to somehow just arbitrarily grab people and their serum and ask that question, there are so many, I think all of you know what the caveats are with placing any kind of serum in a binding assay. Trying to control for background noise would be difficult, and you don't otherwise have a reason for doing that assay. So it wouldn't be unless you had some kind of patient history. Next step would be skin prick testing with purified protein. You would have to have some trigger to start mapping reactivity. Whereas I'd rather, for just an open question, if I don't otherwise know what my molecule is, what's bioinformatics tell me? If that makes sense. Yeah, okay.
Any further questions? Thank you very much.
Well, thanks to Nick and Jeremy for having me here.
We appreciate it.
I might have been here for Mastering Immunity number one,
Number one, yeah.
I think, so it's good to be back. Thanks.
Thank